Hello friends, today we are going to discuss on the successive approximation type ADC, which is a part of the digital electronics. Okay, so let's start today. So this is a circuit of the successive approximation type ADC. Okay, so it is composed of the digital to analog converter, one comparator, and one logic circuit. Okay, as it is a 4-bit analog to digital converter. So we are using this term D0, D1, D2 and D3. So let's see the points, the important points. So see, it is one of the widely used type of ADC. It has a much shorter conversion than the other type. So this is the first point. Second point, it is a 4-bit successive approximation type ADC. We are taking here the 4-bit. So this is the MSB bit and this is the LSB bit. Okay. Third point, the bits of the DAC would be enabled one at a time. Means we have to starting with the MSB bit, following the next significant bit, and so on. So we are starting with MSB bit. First, we have to check this MSB bit. Then we have to come to the second bit, then third bit, then fourth bit. Okay, and the fourth point, which is very important point. This is a very important point. If the DA output, means this output, digital to analog converter output, is greater than the analog input, the comparator output will be low, okay, causing the bit in the control register to reset. Means if the DA output is low, then lower than the input signal, okay, so the comparator output will be low. Means this will become 0, causing the bit in the control registers to reset. Means if it is 1, there will be 1, so after it will be reset and become 0. Okay, and if the DA output is lesser than analog input, if this output is lesser than the input signal, then the comparator output will become 1. So 1 means the comparator output is high, causing the bit in the control register to keep. So if we keep, means if the comparator output is 1, so we don't have to change the value, we have to keep this value. If it is 1, then there will be 1. If it is 0, then there will be 0. We don't have to change the value. And the last point is, all the bits have been tried. The conversion cycle is complete. Means we have to start from MSB and we have to continue till LSB. If the process is complete, we have to check each bit. So after all the bits have been tried, the conversion cycle is complete. So I am going to the illustration portion. See, illustration of the approximation type ADC. This is the heading. So this is the circuit. First this one, second this one, third this one, and fourth one this one. See, we have to check from MSB bit. This is MSB bit and this one is LSB bit. So see, so we have to check the MSB bit. So we are considering this is 1 and the rest of the bits will be 0, 0, 0. So this is a digital to analog converter. So 1, 0, 0, 0. This is in binary. After converting it into decimal, what it will become? 8. 2 to the power of 3, 2 to the power 2, 2 to the power 1, 2 to the power 0. It will become 8 in decimal. So 8. Then we have to what we have to do. The second step is that we have to compare the analog input with this value, with the digital analog converter output. See, the analog input is smaller than the digital converter output, means it is greater. So what the comparator output will be low, and if it is low, this is the point, and if it is low, causing the bit in the control register to reset, means we have to reset that value. Okay, so we have to reset that value. So it is 1, after resetting, what will it become? It will become 0. And next we have to check the next bit. Okay, 2 to the power 2 bit trial. So see, so I am clearing. Yes, see. So this will become 0 as it is. After reset, it will become 0. So I am checking now this second 2 to the power 2 bit. So I am considering this as 1. Okay, and the rest of, and this 2 bit will be 0. So we have to start checking from here MSB, and we have to check it till LSB. So see, this is 1. Okay, 0 1 0 0 in binary. In decimal, it has become plus 4. Okay, 2 to the power 3, 2 to the power 2, 2 to the power 1, 2 to the power 0. Okay, plus 4 is smaller than, as we can see that the digital analog converter output B out is smaller than the analog input. So automatically the comparator output will become 1, means high. And if it is high, it will keep this value. See, if it is high, it will the comparator output is high, it will keep the value. So same. So see, keeping this value. Similarly, we have to check the third. This is the third stage. See, so next, after keeping this value, this will be 0 1, and this will be 1 because we are checking the 2 to the power 1 bit trials. So see, this will, now we are checking this bit, 2 to the power 1 bit. So after, so see, digital to analog converter in the decimal, it is becoming plus 6 volt, and it is plus 5.1 volt. Compare this, the analog input and the digital analog comparator output. This is V out. So you have to compare with the, similarly you have to compare it with the analog input. So see, plus 6 volt is greater than the analog input. So automatically, if it is automatically the output of the comparator is a low, means you have to reset this value. So this is 1. After resetting, it will become 0. Okay, so see, this is 0 1. After resetting, 0 1, and after resetting, this will become 0. Similarly, we have to check this now. So see, 0 1 0 1. So see, 0 1 0 1, converting it into decimal, it will become plus 5 volt. And plus 5 volt is smaller than 5.1 volt. See, 5.1 volt is greater than plus 5 volt. So output will become, comparator output is high, and it will automatically keep its value. If the comparator output will high, it will keep its value, otherwise it will reset. Okay, so see, so I hope you like this video. So this is one of the important topic of the approximation type ADC. Okay, and this is analog to digital converter. So this is the process, how it is converting. So I am ending this video now. If you have any doubt, you can comment me in the comment section, give it below. Okay, or you can mail in my following mail ID. Okay, so